Hi, in this video I'm going to introduce the Weierstrass approximation theorem as an application of the convergence of Fourier series. First of all, we will introduce some definitions. The first definition that we are going to introduce is called the subnorm. What the subnorm is saying is that given a f which map an interval ab to R, and the subnorm of f is defined to be the supremum of the absolute value of fx in the interval ab. The second is called piecewise linear functions. Given f which map ab to R, and it is called a piecewise linear function if there exists a partition a0, a1 up to an such that f restricted to the interval ai-1, ai is linear for I between 1 and n. Third is the triple polynomial. Any triple polynomial is indeed a finite sum of the triple series. And I've written down four kinds of functions. First kind is continuous function. The second kind is piecewise linear function. The third kind is trigonometric polynomial, and the last one is the ordinary polynomial. Well, these four kinds of functions look very different in our sense. But Weierstrass has proven that these four kinds of functions are indeed very similar to each other. And indeed, these four kinds of functions can be approximated by each other with a precision smaller than epsilon, and we will see that these four kinds of functions are indeed very close to each other. Well, first of all, we will claim that any continuous function can be approximated by a piecewise linear function. Formally, we have the following theorem. Given f, which is a continuous function on the interval ab, we claim that for all epsilon greater than 0, there exists a piecewise linear g such that the subnorm of f minus g is smaller than epsilon. And here's the proof. First of all, we know that f is continuous on a compact set. So indeed, f is uniformly continuous on the interval ab. And that means for all epsilon greater than 0, there exists a delta greater than 0 such that fx minus fy is smaller than epsilon over 2, as the absolute value of x minus y is smaller than delta, and xy are the points in AB. And let's suppose x1, x2 up to xn is a partition of the interval AB such that the norm of p is smaller than delta, where p is the partition mentioned. Let's define the piecewise linear function g as gx equal to fxi minus fxi minus 1 over xi minus 1 times x minus xi minus 1 plus xi. And x lies inside the interval xi minus 1 xi. We know that the absolute value of fx minus gx is more than or equal to the absolute value of fx minus fxi plus the absolute value of fxi minus fxi minus 1 over xi minus 1 times x minus xi minus 1. And we know that the absolute value of x minus xi minus 1 is more than or equal to xi minus xi minus 1. Therefore, if we replace this expression by xi minus 1, we will get a bigger sign here. And therefore, this expression is more than or equal to the absolute value of fx minus fxi plus fxi minus fxi minus 1. And we know that these two expressions here are smaller than epsilon over 2. This is because as x is lying inside the interval here, and the norm of p is smaller than delta, which means that the distance between x and xi is smaller than delta. Also, the distance between xi and xi minus 1 is also smaller than delta. So by the definition of uniform continuity above, we know that this expression and this expression is smaller than epsilon over 2, and therefore it is smaller than epsilon. Thus, we have proven that a continuous function can be approximated by a piecewise linear function g. Next, we will prove that any continuous function can be approximated by a trigonometric polynomial. First of all, let's suppose f is continuous on the interval 0 to pi. For all epsilon greater than 0, there exists a trigopolynomial h such that the subnorm of f minus h is smaller than epsilon. So, how can we prove so? First of all, we want to apply the theorem about Fourier series that we have proven before, and therefore as f lies inside the interval 0 to pi, and all the theory about Fourier series are developed on the interval negative pi to pi, we extend f to the interval negative pi to pi. And how can we define the point inside the interval negative pi to 0? We can simply define the function as f negative x equal to fx for x which lies inside the interval negative pi up to 0. So notice that f is still a continuous function. And remember that we have proven that there exists a piecewise linear function g such that the subnorm of f minus g is smaller than epsilon over 2. And you can readily check that g negative pi is equal to f negative pi, and f negative pi is equal to f pi, and f pi is equal to g pi. And I will leave it as an exercise for you to check it. Well, you just plug in the points pi and negative pi to f and g, and you can readily check that they are equal. So, next, also we know that g is a piecewise continuous function. So remember that g will satisfy the Lipschitz condition, and it is a 2 pi periodic function as well, because we have proven that g negative pi is equal to g pi. And by our theorem about the convergence of Fourier series to the function itself, we know that the Fourier series of g will converge to g as n tends to infinity. Therefore, we know that the subnorm of g minus Sng is more than epsilon over 2, where Sng is the partial sum of the Fourier series of g. And we know that Sng is a finite sum of a trigonometric series, and we have defined trigonometric polynomial as a finite trigonometric series. So we know that g can be approximated by a trigonometric series. Now the task becomes very easy. It is because we know that f and g are very close to each other, and g is very close to its partial sum of the Fourier series. So we consider the subnorm of f minus Sng. We know that it is more than or equal to the subnorm of f minus g and plus the subnorm of g minus Sng, and it is more than epsilon as n is greater than or equal to n1, and therefore we can define h as Sng to finish our proof. After we have proven all these results, we are ready to prove the Weierstrass approximation theorem. The theorem states that if f is a continuous function on the interval ab, for all epsilon greater than 0, there exists a polynomial p such that the subnorm of f minus p is more than epsilon. Well, as we are working on an arbitrary interval, we cannot immediately apply our previous result because the previous result only applied on the interval 0 to pi. So we can simply make a transformation. We define phi t to be f of b minus a over pi t plus a. And it sounds weird. Why are we doing this? Well, we know that this straight line here is indeed a straight line joining two points, joining the point 0a and pi b. And therefore, it translates the point A to the point 0 and translates the point B to pi. And therefore, such function here is well defined on the interval 0 pi. And notice that phi is a continuous function on the interval 0 to pi. And by the previous argument, we know that phi can be approximated by a trigonometric polynomial. And that means there exists a trigonometric polynomial h such that the subnorm of phi minus h is smaller than epsilon over 2. And we know that any finite sum of the Taylor series of sine and cosine and their linear combination is a polynomial. And they uniformly converge to sine or cosine on the interval 0 to pi. So the trigonometric polynomial h here can be approximated by a polynomial q uniformly. Therefore, we know that the subnorm of h minus q is smaller than epsilon over 2. Next, we again apply the triangle inequality. We know that the subnorm of phi minus q is smaller than or equal to the subnorm of phi minus h plus the subnorm of h minus q, and the first expression we have proven that it is smaller than epsilon over 2, so do the second expression. Therefore, we get that it is smaller than epsilon. Next, we use the transformation x mapping to pi over b minus a times x minus a. And what is this? Indeed, it is an inverse of the transformation in the first line. Therefore, phi becomes f after this transformation. And also, if we define a new polynomial px equal to q composed with this transformation, we know that the above inequality here become this inequality, which is the subnorm of f minus p is smaller than epsilon. And therefore, we are done with the proof of the Weierstrass approximation theorem, which states that any continuous function can be approximated by a polynomial. And this is the end of the video about the Weierstrass approximation theorem, and I will see you in the next video.